In the previous video, I demonstrated how the concept of color boundness in chess can make it easier to understand certain mathematical concepts such as the Euclidean algorithm and Pythagorean triples. I ended the video with a concept I called the every fraction tree, which links all the simplified fractions in a structured manner which corresponds to steps of the Euclidean algorithm as well as hexagonal chess. In this video, let's start by deriving the double angle formulas. We'll use a night angle as an example. We already know that the trig functions of a night angle are going to be ratios of the numbers 1, 2, and the square root of 5. But when doubling a night angle, it's not so intuitive what the trig functions of this angle are going to be, because the angle doesn't begin at a horizontal or vertical line. But we solve this problem with an operation I call night times night. So, normally night's paths are measured by making two unit vector movements in one direction and then one additional unit vector movement in a perpendicular direction. But the trick here is to construct the night's paths out of night's moves instead of unit vectors, because this creates a rotating effect that allows us to measure the night's double angle with a single measurement. So, by examining the figure on the left, we're able to conclude that 2 times the arctangent of 1/2 is equal to the arctangent of 4/3. But there's not really any way to come to that conclusion if we're only paying attention to the figure on the right, because the angle's not aligned with the rank or file like in the figure on the left. So, if we know the trig functions of some angle, then we can use the method just shown as a way to calculate the trig functions of an angle twice that size. I think that chess variants can help to understand a lot of the intriguing patterns observed in trigonometry, so hopefully now it should be pretty simple to understand the double angle identities. The blue angle in the left diagram represents a general angle, and the red angle in the right diagram represents an angle twice that size.
We can derive half-angle formulas by using the fact that 1 equals cosine squared of A plus sine squared of A, which enables us to rewrite the double angle formulas for cosines in terms of either just a single angle cosine or a single angle sine. So now we have equations describing a single angle in terms of its double angles instead of the other way around. So we can replace the single angles with half angles and replace the double angles with single angles, and now we have half angle formulas.
Next we'll move on to the angle sum and difference identities and observe their connection to complex multiplication and parallelogram leapers. This shows an intuitive look at how to add two night angles together, which we already went over. Next we'll take an intuitive look at a night angle plus a camel's angle.
The original knight's moves make a night angle with the axis, but when the perpendicular knight's moves are made at a camel's ratio to the original moves, it allows us to intuitively measure either a night angle plus a camel angle or a night angle minus a camel angle. The night angle plus the camel's angle ends up at 5/5. The night angle minus the camel's angle ends up at 1/7. So these coordinates 1/7 and 5/5 correspond to the 4 possible parallelogram areas that a knight-camel hybrid can make. So the color boundnesses of parallelogram pieces have a correspondence to taking the sum or difference of 2 unique angles, the same way that the color boundnesses of rhombus pieces have a correspondence to taking the sum or difference of 2 identical angles. Rhombuses are just more specific cases of parallelograms, like how the double angle formulas are more specific cases of the sum and difference formulas. We can better understand the sum and difference formulas by studying the 4 possible parallelogram pieces that a hybrid piece can make. If we do the same things for parallelograms that we did earlier for rhombuses, notice that there's a 4th type of piece we can call flat. Although it's not completely flat because its 2 types of movements are unique, the shape has a little bit of area. Parallelogram pieces have a color boundness that's equal to their area, just like rhombus pieces. These boards show the possible realities of parallelogram pieces with color boundnesses of 1 to 10. You can use parallelograms to generalize the color boundness formula to include hybrid pieces. The color boundness of any chess piece is the GCD of all the areas of the possible parallelograms it can make. You can generalize this formula to apply to the volumes or hypervolumes of parallelepipeds or hyperparallelepipeds. These are the possible parallelograms of a knight-camel hybrid piece. Notice how 5 squared plus 5 squared is equal to 7 squared plus 1 squared. These are the possible parallelograms of a knight-zebra hybrid. Notice the same pattern. And these are the knight-giraffe hybrids parallelograms. And here they are for knight and antelope. These are for camel and zebra. And these are for camel and giraffe. So the flat parallelogram piece always has the lowest color boundness, and the square always has the highest. Even though it's not really a square, we can refer to the parallelogram types based on their corresponding rhombus types. The square of the flat parallelogram plus the square of the square parallelogram is equal to the square of the diagonal parallelogram plus the square of the rank and file parallelogram. When studying rhombus pieces, there were only 3 types of rhombuses, and their areas corresponded to the sides of a right triangle along with the double angle formulas. Now we'll see that the areas of the 4 types of parallelograms have a correspondence to the sides of 2 unique right triangles with equivalent hypotenuses, along with the sum and difference formulas for 2 unique angles. Adding or subtracting a knight angle and a camel angle is going to yield an angle whose sine and cosine functions have a denominator of the square root of 50 and a numerator that's one of the 4 parallelogram areas. So if you understand how to find the areas of the 4 parallelograms, then it should be pretty simple to see the correspondence to the sum and difference formulas. So if you have 2 unique angles, A and B, and you add them together and take the sine of that, it's going to be equal to the sine of A times the cosine of B plus the cosine of A times the sine of B. And notice how these formulas resemble the 4 formulas for finding the color boundnesses of parallelogram pieces. So it's not so hard to understand the sum and difference formulas on the top left when you have simpler things to associate them with, like parallelogram areas. Studying the properties of Pythagorean triples can help to better understand operations with angles.
For example, the information regarding knight times giraffe, which is combining a knight angle with a giraffe angle, is encoded within the Pythagorean triples 138485 and 773685. And notice that the leapers associated with those triples, 7-6 and 9-2, correspond to the 4 parallelogram areas as well as the potential tangents for a new angle, and the 2 unique blue measurements have an identical length that's the square root of 85, and that corresponds to the fact that there are 2 unique primitive Pythagorean triples with a hypotenuse of 85. Many of the intriguing patterns observed here can be better understood with a concept called complex numbers, which allows us to interpret a 2-dimensional point as a single number and can make operations in 2 dimensions run much more smoothly. So, the standard form of a complex number is a plus bi, where a is a point's position along the x-axis and b is its position along the y-axis. The imaginary unit I is equal to the positive square root of -1, and negative I is equal to the negative square root of -1. It doesn't seem like these kinds of numbers should exist, which is why they're called imaginary. I would best describe an imaginary number as the concept of a foreign dimension manifested into a number. So, the imaginary unit I is necessary for distinguishing between the 2 axes, because a big problem with trying to interpret a 2-dimensional point as a single number is that the components of the 2D point are going to conflict with each other when measured in 1 dimension. So by having one real coordinate and one imaginary coordinate, their values won't conflict with each other or imply anything about each other. So it allows for a legitimate 2D number system expressed as a single number. Real numbers and imaginary numbers have an analogous relationship to the x-axis and y-axis. One way to understand the paradox of an imaginary number is to compare it with the paradox, "this statement is false,"